Okay. What is-
You can just share your presentation.
Which one is your presentation?
Yeah, Shito. That is the weird thing.
It's the whole screen. Then there will be.
Yeah, I think I do.
Okay, they keep changing my options on me. Where do you say it
the
went?
top one, I think just go for the top one. This top one, I think that's
No, it's in desktop. What did you say? Who was a suggestion?
go for the entire whole screen.
Oh, just go for
Don't
the
get the instead of any particular.
I can see your screen.
Okay, just change slide once.
Yeah.
Let's just
Yeah.
make sure.
Yeah.
Okay, and then go to more and hide the control panels. So hide video panel and hide floating meeting.
Okay.
Okay, so we are pleased to have Professor Shiladitya Raj Chaudhary as our colloquium speaker today. Professor Chaudhary is originally from Kolkata. He went to St. Xavier's Collegiate School. Later, he did his undergrad from the famous Vassar College in New York State in the US and received his PhD in physics from UCLA. Currently, he is a faculty member of the physics department at University of South Alabama, as well as the executive director of the Innovation in Learning Center at the same place. This center provides strategic oversight and direction for the faculty professional development and support of online learning. Professor Chaudhary's recent publications and presentations have been on faculty development, scholarship of teaching and learning, and STEM education. And as the director of the center, he assists campus-wide initiatives related to measuring teaching effectiveness and implementation of active classroom learning technologies. Prior to moving to administration, Professor Chaudhary was a full professor of physics, and he was also the Carnegie Scholar in 2003-04, and he has been president of the International Society for the Scholarship of Teaching and Learning. Outside of research and administration, he founded and directs the USA Indian Music Ensemble and serves on the governing board of Phi Beta Kappa Liberal Arts and Science Honor Society. So, Professor Chaudhary.
Thank you. Thank you. It's a great pleasure to be here. Both my parents and my sister are all alumnus of presidency in different subjects in physics. And if I had not gotten a scholarship to go to the US, I probably would have come here and studied physics as well. Please come on in. All right, so a quick overview. Just in terms of the talk. In my abstract that I sent to Ritvaban, I said that many talks that you probably have in your colloquia are about learning new physics. This is going to be less about learning new physics and more about challenging some of your assumptions. Extra credit, Francis.
There are chairs that side over here. Now you can move.
Click OK.
Okay.
We had a lot of audience.
That's fine, great. So quick overview of the talk itself. And we're going to actually do some things, right? So that's why I wanted a pen and pencil. Make sure you have a pen and pencil handy, and we will get to that in just a little bit. Yeah,
I need some.
okay. Oh, you need more copy. I see. Okay. All right. So first a little geography lesson, right? So I teach and work at this place called University of South Alabama. If you ever watch the Weather Channel, when the hurricanes are coming to the US, right? Hurricanes usually come like here, they're up here, and that's when we show up on the map. Otherwise, people are not interested where we live, right? But when the hurricanes are coming, they become very relevant. Luckily, most of the time, the hurricanes go to the left, okay, towards Houston, or they go to the right towards Florida. Except September 2020, you all remember that year, right? 2020, big
Yeah.
year, right? All two hurricanes back-to-back weeks came right into this thing. Okay, so we are a regional public university, which in the US means the US is private universities, public universities, and we have some strengths in healthcare, marine science, because we are right on the water, on the Gulf of Mexico, and then systems engineering is a very interesting area. I wanted to talk to you guys because we have at least one space science, space physics type of person who can have PhD students under the systems engineering. So that's a possibility. And I say tropical weather because my mother visited in 2019 in October. It rained every day and it was really hot. So my mother said, why did I leave Kolkata and come here to get exactly the same weather, right? So we have all right. So my academic pathway, and I like to share this in my talks, is like this for many years, right? About 12 years of my life, I was a faculty member for physics. Started the whole kind of physics engine research. Which one of these people am I? And in my observations, right?
You were the last one, scholar of teacher of learning.
Right? But people find themselves, right? These are not discrete states, right? I don't know what the quantum energy gaps are between these different, energy states, but people make this progression. Right? And so I just want to give you a framework we're thinking about as we think about teaching of physics and we think about the people who teach physics. People fall into these categories based on my 30 years of observing this field. Right? So just make a mental note. Yes, Professor X, PPC, this is kind of person, right? SR Shomak, right? There's a big poster of Shomak. Shomak and I went to school together, right? So I know Shomak from the time we went to Xavier school together. He was a couple of years my senior, right? Where do people fall? I showed this at Shomak's current institution, Ashoka University, just last year. So this is a framework, and I will give you. So because in physics, we like to talk about problems, right? We solve problems, right? That's what we're good at, right? That's why we study physics. But I want to give you an instructional problem. And the instructional problem comes from a very, very famous physics textbook author, Fred Rife. I don't know if you guys are familiar. Fred Rife's StatMech. He also had a classical mechanics book, right? But also, lesser known is Fred Rife wrote a lot on intuition. So in 1994, he got the Millikan Lecturer Award from the American Association of Physics Teachers. And what he said, right, essentially, I'm paraphrasing from this time, is that the instructional problem that we try to solve is that students come to us in some initial state, right? I'm just using the state function, right? Some initial, and they have some characteristics, right? Those of you at presidency, you've taken certain exams, you've scored certain marks, right? You have certain aptitude and love for physics. You have all these characteristics, right, that you guys use to select these people. So that constitutes, right, the initial parameters of the state function. When they leave us, they have what should be the final characteristics? Especially as you guys are building a new program, you must have thought about what are the characteristics of somebody who gets an MSc or a PhD, in physics or astrophysics for presidency. What does that look like, right? What are the characteristics there? And there can be multiple pathways, right? So I just want to show there's different thermodynamic pathways that you can get from one to the other. Okay, so just in terms of defining that, right? There's knowledge, skills, belief, and attitude. These are some of the pieces that we need, right? The harder thing to do is, because you can measure these by things like exam scores, right? Or some kind of things. How do they think? That's harder to measure. because just from pieces of paper that you submit in your application. And then the final state, which has to be the decision, it's out of the hands of the students. What is the department setting up? What is the curriculum looking like? What should be the final knowledge, skills, beliefs, and attitudes of students? There is some great research from, very depressing research from the US, going back to University of Maryland, right? It was published in 1996 that showed for students, and these are mainly engineering students, taking a first-year physics class, right? Modules in physics, their attitudes towards physics were more positive at the beginning of the class than at the end of the class. Antidepressant, right? Now, so then, right, this just generated, but we take these as opportunities, right? To do research on why is this happening, right? And how can we change that? Because those of us who love physics, we would at least try to keep it the same, right? If not improve, right? We should hope that our experiences that we give our students in the educational journey that they take should make them somehow have better attitudes towards physics. Because why? Because those people then will talk to politicians who might fund physics, right? If people don't like physics, there's going to be no funding for physics research. So the other piece of work that I'm connecting here is that, well, this is all ancient history, right, for some of you. How People Learn was a great publication that came out in 1999, and it synthesized about 20 years worth of research in education, cognitive psychology, like the learning sciences. And what they did was really talk about people moving from novice states when they come, right? That the initial state of the student is in a novice state. And when they leave, they're closer to an expert state. And there is a lot of research, right, in cognitive psychology, in industrial organizational behavior. What are the characteristics of experts in different areas? So, and we want typically our students, when they leave us, after maybe one module, after a whole course of study, after a PhD, to somehow think more like experts, right, in the field. Shuchit and I was talking about this in the car, right? We can teach you only so many facts, right? But we want you to go away taking those facts and developing habits of mind, right, that will serve you going forward. So mapping onto that the Fred Reif diagram, but now changing the terminology slightly. All right, so we're going to do an exercise on the nature of expertise, okay? So if you've fallen asleep, turn on your brain right now. It's okay, people fall asleep all the time. All right, read this. Let's read quietly for 30 seconds, and then I'm going to ask for some responses. Do I have volunteers? Someone want to raise their hand and volunteer to help answer this question? What is eating disapproval? The cricket loving guy, he's not here today, right? Are you the cricket loving person? All right, so what is being described? Tell us. Who is playing who, first of all? What's happening? What is the setting?
Setting of fielding.
Setting of fielding, okay. What kind of contest is this? Is this kabaddi? It's cricket, okay. Let's start there. Okay, it's cricket. Who's playing who? What teams?
Kohli is batting, Marcel is
England is playing India. Okay. Okay, England is playing India. Okay, let's get one more from you. Let's get one more thing from you. Say something else about.
Jofra is bowling and Kohli is batting.
Okay. Okay. What kind of a match is this most likely? It's most likely a test match. Why? What's the clue?
we sleeps at the others. Things that.
Okay. All right, so test match. Okay, cool. Where are they playing? Lords, how do you know that? The nursery and the Lords, so now you know where they're playing. Okay. Is this early in the contest, middle of the contest, end of the contest?
Probably early.
New ball.
New ball is, so it's probably early in the morning. Okay, so we know, okay, okay. How is India doing?
India back.
Maybe not so great because Kohli is already batting, okay? Okay, can you give me, here's a harder question, can you give me a time frame in years to bracket it, right? What are the boundary conditions on the years on which this could have happened?
Oh, the years, okay. so-
Years, right? So it's slightly deeper knowledge, right?
Yeah,
Kohli's been around for a while,
yeah.
but Archer has not.
2019, 2018.
Okay, then what happened? Okay, okay, it's okay. But then 2020 probably not because not much cricket was being played on here. Okay,
In my
COVID year, yeah.
then what happened to Archer shortly thereafter? He got injured. He was out of cricket for like 3 or 4 years, right? He's not playing Test cricket right now. They're giving him like 4 overs and then T20, right? So now so we have bracketed this. Anything else anybody wants to add? Can you predict a likely outcome? Out, okay, you have no faith in Kohli, right? So you can now, based on the basis of this, you can make a prediction of the next thing that. Right? What I want you to think about, think about all the expertise in this room, right? That when I show this same thing in America, what do they say? Cricket. Somehow everybody knows cricket. After that, silence. Silence. Okay? Unless there's some Indian people in the audience, then then they might be able to have a chance, right? Here we got all this, right? All of this stuff, right? You know about the roles the teams are in. You can tell me what sport it is, what teams are playing. Right? You can probably give me an account of those locations, those names, right? The fact that those names, right, are actually these locations, right? If I give you a piece of paper and this text, many of you here could draw me that diagram, right? So you could take a textual representation and give me a visual representation. You could draw a diagram essentially, right?
Because of the knowledge.
And that's the expertise, right? This is this inherent expertise. Sound good? Okay, so these are some of the things that experts can do, right? We can do all of these kinds of things. All right.
Fixed term is going.
All right. So Ritaban may know something about this one, but okay, what's happening here?
Baseball.
People said baseball, okay. Same things, tell me more. Who's playing who? H is playing B, right? H is playing B. All right, you remember the B from your time?
We are here, but I have to think of it.
Okay, can you help us?
Boston Red Sox.
Yeah, that's.
Boston Red Sox, okay, we got from Professor Ritaban, okay, very good. H.
Houston.
Houston, okay, you can pick a random city in the US with H, could be. Houston actually is correct, okay, very good.
Houston Astros.
What sport? We've got baseball, okay. How about this is early in the contest, really? Early, why? Why do you say early? Score 0-0?
That doesn't get
That doesn't necessarily get that.
the one.
It's one thing, okay, this one thing. Who's batting? Or
Probably Boston's back. Go on the.
we don't know, right? There's some Boston. Why do you think Boston? Red sweater, yes.
Just like the one and the number of dots and the first one has been done the yellow sun. I'm assuming.
Okay. Okay.
Yeah, one strike and 2 are remaining.
Okay. All right, 1 strike, 2 are remaining.
And 2 are
Okay.
on base.
There's 2 on base. Okay, so there's 2 people on base. So if I think about location of players, right, 2 of the bases in the diamond will have occupied by these 2 people. Okay, so here's another thing, right, about the fundamentals of how this is done is that in the US, it's always written Houston Astros at Boston. Okay, Houston will always bat first. Your away team always bats first. There's no point us at the beginning to determine who bats based on the pitch, right? Like in cricket, the away team always bats first.
So
Okay,
it's been played in Boston.
it's been played in Boston, so that's right. It's been played in Boston because Boston is below. And this little up thing means it's the top of the first inning, which means Houston is batting. They're at the top of the inning. And then when Boston is batting, it's called the bottom of the inning. Unlike in cricket, which is innings, and baseball is called inning. Is this an important match?
Yes.
Okay, tell us why you think that.
There is the ALCS championship. So that's
ALCS. Okay, what does that mean?
American League.
Championship series. Okay, right? It's like semifinal for baseball. Okay, and is it being televised?
TBS.
TBS.
TBS is a
That-
is a television channel. You know the TBS.
That one.
Right, so just imagine the contrast between how we worked through our cricket thing versus our baseball thing, right? So this kind of all goes back, right? So here's just to fill you in. Baseball, Houston Astros versus Boston Red Sox, right? There's another subtlety here that I ask American audiences, which is like, I won't ask you, is give me, let's say, bracketing of time when this could have happened, right? And it turns out that Houston used to be in the National League, and this has to have happened after 2013. In 2013, Houston moved from after you left the country, they moved from the National League to the American, right? So it could not have been an ALCS prior to 20. It's another subtlety also. But timelines are important, right? We need to know when things happen. So, all right. So all of that to say, right? So what's the research? Going back to the research is really these are just some of the characteristics of this, right? That has come about from looking at a lot of these kinds of data, right? Notice the features and the patterns of information, right? You guys picked that up in the cricket really very easily. You have the knowledge, the knowledge that's organized. You have schema for your knowledge, right? And your schema for cricket as a group was obviously much better than your schema for baseball, right? You were randomly guessing at stuff in the baseball. Cricket, there was a lot more deliberation. It's like, yes, I know this, right? This is what is. And the same thing. Some level, my wife asked me this morning as we were walking by a cricket match in the Taqueria Lakes, we're taking a morning walk. Some level, cricket and baseball, they're cousins, right?
Yes.
There's a ball, there's a bat, you hit it, you run places, and that's how you score runs. So you have to score more runs than the other team too. So at some level, right, they're cousins, so they're similar. But the context of applicability, general knowledge about balls and bats and running around bases doesn't get you specific knowledge to apply to the baseball, right? The athletes have to be similar. You have to be fast when you run from one base to the other, from one wicket to the other, right? You need, when you're delivering a ball or pitching in baseball, you need to have good arm strength, right? You need to do things, the ball has to do funny things, or else the batsman will hit it. These things are the same, but many other things are not. And then this is what used to get me when I go see my physics professors with a problem. They were able to retrieve, right, aspects of knowledge so easily. Like, how did you, I struggled for 3 hours with this problem. You go to see the professor, they solve it in 10 minutes, right? And you've all been through that. All right, so just, once again, in terms of resources, a lot of my resources, they came from this book, nap.edu, that National Academies Press. It's free, you can get the book there, right? And the other part that they talk about, because when Professor Roy Choudhury Shomok was here as HOD of physics, we had some discussions about, maybe it was before you guys got here.
No.
You were here
Yeah,
when I first came?
Yes,
Okay.
he's the one who got us here. So he
No,
left
no.
in 2015.
No, is it?
I'm saying I talked to him, I think maybe before you guys had gotten here. Anyway, we were talking about, he was thinking about, because Shobhashati was here. Yeah,
Yeah,
Shobhashati was here, right? Shobhashati was here.
Same.
Okay, perfect. Anyway, the thinking about like what should classrooms look like, right? And then you have the physical classroom, but then what is the learning environment, and what's the research tell us about effective learning environments, especially for difficult subjects like physics, right? And so this is some of the research, right? Any learning environment has to be knowledge-centered, right? Learner-centered. Those of you who studied physics, you've probably seeing the same phenomena. Let's say Newton's laws, probably start in class 9 at some very basic level. And as you go through the levels, right, you get more and more sophisticated thinking about how to apply things like conservation of momentum, right? Conservation of energy, that's what's more sophisticated. Right? But the learner has to be part of the learning process. Otherwise, it's just delivery of instruction and no learning. assessment centered, right? Really thinking about, right, how can I get an understanding, right, that my lesson, my lecture, my lab, whatever it is, the practicals that you're doing, that they're actually leading to learning. And then finally, this is a big part that I've worked on in a number of settings, is community centered. One person can sit and read a book, and maybe some people are brilliant at reading just a book and learning everything from it. But for many of us, the preponderance of research is that, right? Learning and social construction of knowledge and the community aspects of learning are very important to learn as well. So 2018, there was an update to the How People Learn book, How People Learn 2. And so we still have that same, right, the graph that I showed you earlier, the progression of novice to expert, right, with those multiple pathways. What How People Learn 2 did, right, is that it added beyond the cognitive. So How People Learn 1, the initial one we talked about, was really focusing on cognitive, which is the brain working, right? How does the brain process information, right? How do you learn certain things purely from the cognitive basis? But what the next 20 years of research really showed us is that in addition to the cognitive tools that you have to do, especially subjects like physics, right? These other things come into play, right? There's social aspects, there's cultural aspects, right? We've been talking about women in science, right? For a long time, women in physics, people say, oh, you're a woman, you can't do physics, right? This kind of an attitude, hopefully it's not as bad as it was, but that's a compressor. So that's now a societal cultural pressure on somebody trying to learn, right? And then there's biological context as well that come into this. And so really, right, if we want to understand about how people learn, just focusing on the cognitive, right? And that was the exercise we did with the cricket and baseball, right? We're really thinking on the cognitive pieces of that, right? That's not enough. We have to do it. And this is what got me interested in terms of leaving physics and moving into. So I'm going to go back to this particular one, right? But the job of the physics professor just got, right? Because this was all just focused on the technical aspects of physics. Already there was a lot to think about. But now I want you to go back in your brain and think about some of those professors that you thought about initially, right? Is that which ones, right, were also helped you with some of these other aspects, navigating that. And especially as you guys are trying to have PhD students, right? That's a long journey, right? So these factors become bigger.
Then more important.
Right? So tough job, but a great job with great rewards. So in my abstract, I had promised that I would mention some of the Boyer, and I do want to mention a little bit here. So in 1990, Ernest Boyer was the president of something called the Carnegie Foundation for the Advancement of Teaching. And the Carnegie Foundation was important because they set a worldwide standard, international standard, not just US, international standard, for really thinking about the priorities of the professoriate. What are the priorities of the professoriate? Because people's roles in universities, being a professor in a university, especially in the global age that we live in now, has many dimensions to it. And one of the reasons I gave this talk, and I love to see, younger emerging scholars in the group, is because I hope some of you will consider, but ultimately going into academics and keeping this group work. So Boyer's premise, right, which is an interesting premise, is like, what does it mean to be scholarly, right? And one of the findings that he writes about in his book, which I think is really interesting, is that the word research, right, only actually entered the vocabulary of higher education. Research as we know it, right, only entered the vocabulary of higher education in the 1870s. Okay? Actually, if you go back before that, many professors in many places were teaching just with a bachelor's. So this whole idea of conducting original research, right, getting to a master's level through original research, getting to a PhD through original research is a very, very new concept, right? 150 years. It's not that old. Especially in American higher education, 1906 is when it was introduced. Daniel Point Gilman, some of you may have heard, especially in your area, Johns Hopkins University. Johns Hopkins, very big, right? In astrophysics and stuff, it's a very well-known university. But he was the president of that. And that university was the first one to offer the research-based master's degree. So it's relatively 1906.
1906.
Okay, barely 100 years old. It's not that long. And what's really interesting is that the word scholarship, which doesn't translate into very many other languages. One of the things Ritaman read to you was I was president of a society called the International Society for the Scholarship of Teaching and Learning recently, right? In 2022 to 23, I was the president. It's an international organization, people from 30 different countries all over the world. I challenged them to translate the word scholarship as it is meant in English, more broadly, into their mother tongue. Bangla হয় না. Panditya is not the same. Pandit is reading a level, right? Panditya is a manifestation of scholarship, right? But the journey, right? Being engaged in that. Right? I've had discussions with West Bengalis and Bangladeshis about this, right? This kind of thing. Haven't quite gotten there. In many other languages, right? We know scholarships in terms of financial scholarship to aid study, right? But scholarship. And so the contribution of Boyer that I wanted to share with you guys especially is that he talked about scholarship. Right? Scholarship is something that university professors, university academics should be engaged in. However, especially in the context of US higher education, the kinds of things that we do is that there's lots of different kinds of scholarship. These four were the main categories. So discovery of knowledge, right? This is the one that you know as research. Okay? That's definitely important, right? Some of you are doing fundamental research in astrophysics. I see you guys post on Facebook about really cool stuff that I don't understand, but I'm like, yes, it's great that you guys are doing this great fundamental research. But there's also work to be done, the scholarship application of knowledge. Right? How do we take, right, some kind of a finding in one area and apply it somewhere else? Right? People did work in fundamental work in mathematics, and then that fed into something like fluid dynamics, right? That was an application of knowledge in another area. You can be doing work in algorithms, which then have some application in an app, right? That somebody's actually able to use. Integration of knowledge, we're actually going to do a little exercise with that, and then scholarship of teaching and learning, right? Because the act of of teaching is a scholarly act. And this was important because sometimes in academia, this activity is provided higher status, higher privilege than some of these other activities. And my crusade, right, right now is to say that this is a plane. It's not a hierarchy, it's a plane, right? It is really a two-dimensional plane. That's an XY plane, and people can live in one quadrant or the other, right? And no one quadrant is better than another quadrant if you think about a Cartesian coordinate system, right? All of the quadrants have their particular value, right? So that's what we're going to talk about a little today. So I just want to share this with you because what does scholarship actually mean, right? So a concrete way with some examples, right? That if you are doing, because people do all kinds of activities, but what kind of activity, we're funding the thing, right? What is the activity, intellectual activity that should qualify as scholarship, right? So here is from my colleagues at the Carnegie Foundation provides this, right? And if you think about really good work in any area, we know that this typically goes along with research, right? Traditional research, we want it to be peer reviewed, we want it to be duplicated, replicated, right? It should be documented. We sometimes don't pay as much attention to the creativity, right? Creative solutions are crucial to do original research. Right? So creativity needs to be part of it. You can't just copy somebody else's, right? That's not scholarship, that's plagiarism. And it should be significant to the profession. Right? So that box goes into scholarship in defining what something is scholarship is. Okay, so we are now going to do an example. Okay, and I think I am ready. Just give me 1 second. Yeah, let's start handing this out. Okay, So the particular activity we're going to do, there's something called interactive lecture demonstrations. Was started by this group called Thornton and Sokolov. It's been around for a while. I have not been actively teaching physics for 15 years, right? Because I've been in administration. So that's why all my examples are really old, okay? But they are oldies, but goldies. They're still goldies, right? They still address some fundamental, really good parts. Okay, so in an interactive lecture demonstration, typically in a classroom like this, I would have some equipment to do a demo in the front of the room, right? I would probably use ICT, some kind of ProQuare ICT to collect data from my experiment, right? It would be a whole class shared experience. Everyone would see me do the demonstration together, right? There would be a prediction phase and a results phase. And there's lots of research to show that not only does it increase student engagement, that there's actually increasing conceptual understanding.
Okay, so if there are many in the same row, then just pair with some other row. For example, I will be one.
I'm going to disconnect for a second and set up my demo. Okay, just give me a second.
Not everyone, at least one or two in a row, right?
Borrow your sheet for a second. Thank you. Yeah, I've just created the projector. I'm sorry. Yes. Oh, okay. Yes. I didn't have time to set up my demo. All demos need to be set up well. Okay. Thank you. All right, let's reconnect. Okay, so this room is small enough that if I did a physical demonstration here, most of you would be able to see it. But the young lady in the back, you probably don't, you have to stand up, right, to be able to see it, right? Can you imagine you're doing a physics lecture in a room with 250 people, right? Okay. And so then professor has one demo in the front, people in the back, it's like distance education, right? This is really far away, you can't see it, right? It's like this. So sometimes even if we believe in physics that physical equipment is better, but sometimes to actually get to the educational benefit, using something like an app, do a simulation that you can, if I can put it on the screen and everybody can see it better, the engagement's going to actually be better. Okay, so this is, guys, called the Moving Man. Okay, you can go and find this yourself and download it. It's okay, it's fine. It's okay, I'll stay out of the way. It's okay. The floor is not too dirty. Okay, so this guy, okay, I can give him simple kinematics, right? I can give him an initial location, right? I can give him some initial velocity, okay? And I can give him maybe a little bit of acceleration. Okay, negative acceleration. Okay, fine, right? And so the way this works is that I click the button and he will go, and then at some point he turns around and he goes the other way. And he should speed up, right? The negative acceleration is very small. That's why he's speeding up very slowly. Everyone at the end? There's a sound effect. Okay, all right. Right. You have to have sound effects. There's 250 students, you have to keep them entertained a little bit, right? So that's important. Okay. All right. So you have on your sheet, right? This blank, right? So initial position is 5 meters. You can write that in the little left-hand box, right? His initial position's 5. Let's put a 5 there. Initial velocity is negative 2.4. So in the velocity first puts negative 2.4. So 5 position, negative 2.4. Acceleration is positive 0.4. Okay, plus 0. Need to do one more thing. Okay, so when I hit that play button, he's going to move based on these parameters. Right? What I want you to do is sketch what is these 3 graphs going to look like. What's the position going to time going to look like? What's the velocity versus time going to look like? What's the acceleration going to time going to look like? And you have should be about 12 seconds on the about 11ish. So 11 to 12 seconds. So the simulation is going to run for about 12 seconds. So that's your time. Time equals 0 to time equals 12, right? Initial position, velocity, basic laws of kinematics. Go. If you've forgotten the equation, like I said, if you like words, right? Different representations, right? Could be a formula representation, could be text representation. At the end, I want 3 lines, right? There should be 3 lines, 1 on each line. You have to get it. Next people that start working. Question comes. Two more minutes. 2 minutes, 2 minutes. In the high school physics, just to remind everybody, right? We all did this in high school. My first one. So from what I saw, some people, right, are attacking this from a conceptual basis, right? First principles. And a half 80 squared actually means it has to be a parabola, right? So the position, there should be a parabola in the position versus time. It should be some kind of parabola, right? It should be some kind of parabola, right? Other people I heard say that, okay, the acceleration is constant, it's just a. So what kind of graph will this be? Just a flat, straight line, right? Flat, it does not change with time, right? The acceleration kinematics is not. So then the tricky question is what happens to the velocity, right?
Straight line.
Straight line. Okay. Talk to people on your table, right? There's just, let's get everybody getting, you might have somebody next to you who has the blank children, right? So what I want everybody to commit to some kind of a graph on your paper, right? Make the commitment. ভুল হলে ঠিক আছে. You must make the commitment, convince your brain, right? Just like Kohli. Kohli's going to push. I'll forget about it. All right. In the interest of time, would you like to see the actual result? Right? You have some graphs on your paper? Okay. Good. As I said, empty paper চলবে না, but some kind of graph. Okay, good. All right. Okay. So let's run it. Okay, we're going to run the simulation. Okay, so run the simulation, right? Are you not eager to find the results of the simulation? You're probably really eager, right? Okay, here we go. Ready? Right. -2.4 -2.3. I really get that there. Absolutely. Good. Okay. Okay. So obviously I didn't come here to teach you some very basic kinematics, right? You know that, right? But I wanted you to think about it differently, right? Think about it differently. And now just the exercise really is here. I got you to commit, right? The important thing, it's very, very hard to say, am I going to get it wrong? But cognitively, right? As you work through your higher levels of physics, commit to your answer, right? Your professors would want you to have say, okay, I've thought about it. I'm going to make this commitment. If I'm wrong, okay, I go back and correct it, right? And so imagine now doing this with 200 students, right? What I do is I collect the prediction sheets. And then after that, I give them essentially a results sheet to take home so that they can then, have the correct answer, right? So I will give them another sheet, just like this one. It says results on the side. And when I run the simulation, they copy that down and they take that home to study. But this one, I have proof in the class that they tried, right? Because if you don't commit, that your cognitive senses are not engaged to the point where you learn, right? Because good physics professors, right, are very good at explaining things really nicely. That doesn't help you learn. Your brain's got to get engaged, right? Okay, so I'm going to rush a little bit here, but the reason that I've gotten really interested, and I'm still doing this activity, I have done this on 4 continents, same activity, right? In September, I was in Peru, South America, and we did the same thing in Spanish, right? Same activity, okay? So actor scripts and orchestration, what does that mean? Well, this is an active learning thing that we did, right? This is in the general category of active learning in physics. And I borrowed some work from some people in Lausanne, in Switzerland, and Spain. And the activity that we did is called on the side of your face is ILD. ILD means interactive lecture demonstration. That's what we did, right? It was a lecture, it was a demonstration, right? You didn't do practical hands-on, it was a demonstration, but it was interactive, right? You had to make a prediction and then we got to see the results, right? So that's the learning part of it. So we have a script, okay? And then the script specifies, right, how we should do this. It talks about, well, we have materials, so we had to have the pencil and paper. Ritawan got us the materials, the handout equipment, right? And then, right, you had some individual, some group work, right? And then we had some learning activities. The more interactive you become, right, it's more work for the professor. What did I do? Can someone describe what I did while you were working on this thing? Student, what did I do? Did you notice what I was doing?
Prepared the thing.
I prepared the thing.
You
Okay.
were observing.
I was observing. Did I interact with you?
Yes, you asked you what method they were.
What the method you were using, right? So I have a role as well, right? So I'm also an actor, cooperating actors, right? So we are all actors in this play. It's like a Shakespearean thing, right? We are all essentially on the world stage, but we all have our roles to play, right? In this particular action. And then the orchestration, right? Knowing how long do we go, right? In each one of these things. So that is this area of doing orchestration. And so this was the script that actually we went through, okay? And then see, normally I would have you turn in your sheets, and but we're moving on here. So there is a script, and then there's considerations, right? So because a class period, how long are the class periods here?
50 minutes.
50 minutes, right? 50 minutes, same in the US, right? 50 minutes is not a lot of time, right? Because I have to figure out, okay, how long is this going to take, right? If students come in late, like they did, right? What happens? How do I accommodate for late students, right? What aspects of the demo will work? How do I do this? These are all aspects of orchestration. Just like doing orchestra, symphony orchestra, same kind of idea, right? How long will I give you for doing your work, right? Where do I do? What do I do? Do I stand in the front of the room or do I walk around? In a lecture, it's pretty easy. Professor stands in the front and lectures, right? In this kind of thing, I have to think about, can I get to the person in the back corner? Do I have to climb over some seats to get there? How do I talk to everybody? But these are actual practical considerations in teaching, right? And at what point? Some of you still had blank papers when I realized, okay, I think 80% of you have some prediction down. It's time to move. If I wait for 100% of people to complete their prediction, we'll be here. But these are decisions. These are decisions that have nothing to do with physics, but have to do with good teaching, right? How do you make those? And every professor makes that differently. All right, so this is part of the orchestration. And the thing I want to show you, I've been showing you a lot of research done by other people, right? But I have done some original work as well, which is nice. And so this is one of the things that I've built, which is what's called an orchestration graph. Like all good physicists, I love graphs, right? So I'm just going to show you this graph, right? This is the activity, and it's in a loop because I made in a 50-minute, I might do 2 of these. Right? So it's just a loop, the same thing with the same activity. Okay, so first, whole class demo. Remember I showed you the man just by himself walking? That was the first class demo. Then what happened? I asked you to make the predictions, right? Then there was some opportunity. I asked you to talk to the person next to you. Some of you had to work in a small group because of that. Then you finalized your predictions. And then we did the whole class, right? The instruction facilitates. We had some description, some discussion. Some of you may say, this is going to be like this is going to be like this. We did, number 6, we actually did the demonstration. I ran the simulation. We looked at the results. You would have filled out your results sheet at this point and taken it home. And then, I would offer some conceptual insight. So that exercise that we did in about 15-20 minutes, right, all encapsulated in a diagram. And this has become very important to explain to other people. Because if a professor comes, like an HOD, comes to watch you teach, and they say, Raj, I went to your class and you weren't teaching, you were just walking around talking to the students. How does that constitute teaching? Then I can show this, right? because this is actually the schemata of what I'm doing in my teaching. It does not involve me standing in the front and delivering an eloquent lecture, which I could do. But, right, if somebody walks in who's not familiar, I need to have something to share with that person, right? Especially people like HODs and deans who may not understand how this research-based physics education might be going. So I have built some of these for different parameters, right? This is intellectual lecture demonstrations. There's other active learning techniques for which I have built several of these orchestration diagrams, right? And actually, I showed this at the Women in Physics thing online last year. All right, so I'm going to finish with something. Give me 60 seconds. I left this country in 1981. Right? I was 18 years old. So I've been gone for over 40 years, right? There are parts of my identity that I've held on to, right? And as you go through life, you will have many aspects of your identity, and society at different levels will challenge certain aspects of your identity. So I want to share a little bit of my identity journey with you. Okay, one of my identities is as South Asian male with a PhD in physics. Many places, right? I'm actually giving a talk about a poster session on this same thing that you guys are doing. That gives me privilege. People say, "Oh yeah, you're a doctor, very good. You can do this, that. I'll give you a research grant, whatnot." Okay, so that's one part of my identity where being a male, especially Indian male with PhD in physics, people accept that no problem. There's another thing that I do. Okay, all right. This is a couple of years old, obviously, right? But I'm a football referee. Okay, and I'm a pretty serious football referee, right? Does football referee, the spectators care if I'm Dr. Chaudhary?
No.
No, right? Referees will get abused, right? So you are a blind, you are a everything, all the things that happen, but it's still me. So I still have to navigate that part of my identity, right? And then finally, even though I live in a state like Alabama, I actually continue to practice and teach Indian classical music, right? Okay, in a place like Alabama, right? And there, nobody understands Indian classical music, right? So you can see among my students, right? There's some Indians, there's some white Americans, right? And being able to do that, that's part of my identity that I have held on to, right? Even though it's childish much later. And then one other thing, these two arrows, these are other identities. Some of you are too young to have these, but these are my daughters, right? And so another part of identity, right? And I've been lucky. Both of my daughters actually still talk to me, which is nice, right? And they have also engaged in these activities that are part of my identity, right? So as you grow up, have children and stuff, think about ways in which you connect with that next generation as well, right? But that's because my identity as a father is also an important part of my identity. So how to make all those things work together is a big part of it. So thank you guys very much for having me.
Okay, question?
Yeah, but I have actually the thing that you have given here.
Yeah.
There's a little bit of numerics also required. I mean, to make it right? Then this should be a proper graph paper. Then only you can have a y-cut, the straight line equation for the velocity, right?
Right.
But then what should be the time cut and what should be, there is a little bit of, and also this parabola thing. Also, what should be the focus and all. There, one needs to have a proper, because that's numerics. So you have to 2.4 by 0.4, something like that you will do. So then, so this is perhaps the train in which the position will go. This is perhaps the train that you were trying to do. Yeah.
So I think you're absolutely correct. So part of what we have to think about is, what is the point of the exercise, right? Is the point of the exercise to have an accurate graph, or is the point of the exercise to challenge things to students to think conceptually, right? So the part that you said, T-square it has to be a parabola. Maybe that's a very basic place where I want students just to be able to have that instant retrieval of that expert knowledge that you have, right? Which some of these students struggle with, right? They haven't quite gotten to that level of recall in terms of their schema, right? Of what the T-squared means in terms of what the graph's going to be. So then for me, getting the shape The fact that it should be a parabola and have an inverted parabola like that,
Right.
that's much more important than the specifics, because I will follow up with a practical exercise when ultimately want each one of them to do that with collect their own data and then do a more mathematically accurate. So great point. Thank
So
you.
it's the question of what I want to see that what the students have learned.
Yeah. And in a short, right, in a session like this, the shape is much more important.
Yeah. the calculation.
But it's interesting, many of the students here, and I did this recently at Purdue University in the US. There were 2 Indian grad students. Guess what? They went to get the formula and started to generate the numbers, right? That was their default. They wanted to generate 0, 0.1, they wanted to generate a number table and then plot that. That's where their mind went first. So there's multiple ways, right? That's the other thing, multiple ways of attack.
Other questions?
Any other questions?
Yes.
Is that right?
Sir, my question is how
Hold
do
on,
you manage,
guys, shh, that's this.
how do you manage so many things last we saw? What is the
Just no sleeping.
Right, all of those things didn't happen. I'm a Buro, right? So I've had many years on this earth. And so these things have developed over the years. The thing I've held on to throughout is the music, right? So that's taking different forms. For many years, I just used to sing at home and practice at home, did not do formal teaching. But last 15 years, almost by accident, I started teaching Indian music and in the university setting, because that's a university class, elected class.
Oh.
Okay, that's actually elected class, yes. So students can take from physics students, engineering students.
Yes,
South
yes.
Alabama, yes.
Actually, that also is a classical music.
Okay, let's talk a little bit.
Other questions? Okay,
So I think I have a question, but that's not related to the talk, but is related to the discussion that we had in the car, that
Yeah.
you are now developing a module to train HODs on how to hire good faculty. Is that?
That is absolutely correct. Yeah.
It's not.
That is right. So,
And like, what are the things that?
sure. So, in hiring, at least in the US context, right? Indian context is different, right? But the reputation of the university is important in attracting good candidates, right? The infrastructure of the university is important in attracting good candidates, right? At our university, faculty salaries are lower. Okay, each university, there's no national scale, right? So each university has different salary scales, right? So part of what we're doing is trying to have HODs be able to list out what are the strengths of coming to a university to teach. For instance, our classes are smaller, right? Because it's a smaller university, our classes are smaller. So you might teach 24 students in physics versus 240 students, right? So that's a benefit, right? We have internal incentive grants, right? HODs are hired sometimes from outside with no knowledge of the university. So how do we get the HODs up to speed on that? And then the other big part, so we have a faculty handbook. It's like a union guide that shows out the responsibilities of the HOD. One of those is, how do you properly evaluate teaching?
Yeah.
And so that's why I brought that point up about, show this graph when the HOD doesn't understand what you're doing, right? To show this graph, because evaluation of effective teaching is another HOD responsibility that they never get any training in. So that's another part of our module, right? What does it mean to observe a class? What does it mean? How do you talk to the students and get feedback from the students, right? What's valuable feedback?